Alright, so let's look at this example. In the last class, what we had done was that given any linearly independent set, we had this Gram-Schmidt's orthonormalization process, which gave us something in the sense that we got a set of linearly independent vectors which were orthonormal, and the linear span was maintained at each stage. Fine. Now here we are asking a question, let S be this set. This is linearly independent, that you can check. Fine. And then I want something such that the linear span is maintained, but the T set is orthonormal. So there are two ways of doing things. So let's look at the solution of this. Fine. One is that you take U1 as 1 minus 1 1 1, U2 as 1 0 1 0, and U3 as 0 1 0 1, and apply Gram-Schmidt's. So, but my question here is that I just want Ls of S to be equal to Ls of T. At no place we are saying that I have to maintain the linear span at each stage. In the Gram-Schmidt's process, there was this linear span of U1 to Ui was same as linear span of W1 to Wi. I am not asking such a question here, alright. So therefore I can change the order, so I will change the order. So define for me U1 to be equal to 1 0 1 0, U2 to be 0 1 0 1, and U3 to be equal to 1 minus 1 1 1. I want to write this, alright. So now if I look at inner product of U2 and U1 is nothing but 1 into 0 plus 0 into 1 plus 1 into 0 plus 0 into 1, which is already 0, and therefore U2 and U1 are orthogonal. So I don't have to worry about finding the projections and so on. So I can just define my W1. So define W1 as U1 upon length of U1, which is nothing but 1 0 1 0 divided by root 2. Similarly, W2 you can define as U2 upon length of U2, which is nothing but 0 1 0 1 divided by root 2. Fine. So I have got these two vectors which are perpendicular and they are of length 1. Fine. I am not writing them as column vectors because I will have problem in the space here. So therefore everything I am writing in terms of rows, but basically they are column vectors. Alright. Now I have to look at what is W3. So need W3. So we look at what is called V3. So what was V3? V3 was U3 minus the components in the different directions. So this is the component in the direction of W1. Similarly, I have U3 minus W2, W2. So remove the components in the direction W1 and W2. Alright. So U3 is given to be 1 minus 1 1 1 minus, you have to take the dot product of U3 with W1, U3 with W1, so it is 1 1, so it is 2 I hope. So 2 upon root 2 comes twice, 2 here, fine, and it is 1 0 1 0 minus U3 with W2, so U3 with W2, this is U3 with W2, which is already 0, 0 times this, 1 minus 1 0 1, so it is already 0 here also, alright. So this is 0 upon 2 times 0 1 0 1. So therefore I just have 1 minus 1 1 1 minus 2 cancels out, it is 1 0 1 0. I hope I am doing it correctly. Yeah, it is correct. So this minus this is 1 minus 1 is 0, minus 1 minus 0 is minus 1, 1 minus 1 is 0, and this minus this is 1, so I get this. So this implies W3 is equal to V3 upon length of V3, which is nothing but 0 minus 1 0 1 divided by root 2, alright. So for me the set T is nothing but W1, W2, W3. Is that okay? So I took an easy example. Let me take another example. Second example. So I am giving S as V1 which is 200, V2 as 520, V3 as 310, V4 as 111. Fine. I want the same thing, that want an orthonormal set T such that Ls of S is same as Ls of T. All right. So let's try to do that again. Solution. Fine. So let me do with V2, V3, a complicated one, and then build up ideas. All right. So I was starting with this. So for me, this is my U1, this is my U2, this is my U3, and this is my U4. All right. I am trying to look at that part. Right. So for me, since U1 is this, so I define my W1 as U1 upon length of U1, which is equal to 520 divided by 25 plus 4 square root, 25 plus 4 this, which is same as 520 divided by root under 29, I hope. Fine. Now I have to define V2. So V2 is U2, which is 310 minus dot product of 310 with 520 into 520 divided by 29. All right. Because unit vector, so root 29 will come twice, I will get this part. So this will be equal to 310 minus 3 into 5 is 15, 15 2 17, 17 upon 29 of 520. So this will be equal to whatever it is, 29 to 3 is 78, I hope, and then it is 29 0 minus 17 into 5 is 85, that 34 0 divided by 29, which is same as 78 minus 85, I think is 7 with a minus sign. Then 29 minus 34 will be, I think, minus 5 or minus 5, 0 divided by 29. I hope it is correct. Please check it out, question mark. Fine, whatever it is. So I define my W2. Define W2 is equal to 570 divided by 25 plus 7 into 49 square root, which is 570 divided by 9 5 14 4 2 6 74. All right. So please check. All right. Verify. That is your question, that you please verify it yourself. Verify. All right. So you can define W and W2. Do it yourself. Now let's look at W3. W3 is U3 minus U3 W1 minus U3 W2. Fine. So I am claiming that this is 0. Why this is 0? Because look at V2 and V3. All right. So what we know, linear span of U1 U2 is same as linear span of W1 W2. Fine. Linear span of U1 U2, if you look at 520 and 310, it gives me the xy plane. So this will also give me the xy plane itself. Fine. And U3 is nothing but 200. This is my U3, which belongs to the xy plane, and therefore implies that U3 belongs to linear span of W1 W2, and therefore, sorry, this was my V3. V3 was this. So I get that V3 is 0. All right, and therefore I don't have to do 3. So as V3 is 0, we don't have U3. Is that okay? U3 at this stage. Fine. This is what you have to be careful about, that when you are doing things, if the earlier set was linearly dependent, you will get a corresponding dependence at that stage itself. So, u1 and u2 are independent, so you got w1, w2. u3 was dependent on u1, so u3 belonged to the linear span of u1, u2, and therefore the dot product or the component will be 0 here. For example, we had this 0, and this is what is going to play the role. That understanding is very important. Fine. And now you can compute u4, you can use your u4. So, now use u4 to define V3 as u4 minus u4 w1 w1 minus u4 w2 w2, check, V3 is not 0, define your w3 is equal to V3 upon norm of V3, all right. So, I leave it for you to do all these calculations yourself. Is that okay? So, this is what you need to understand, that you can do things on your own, you are good at it, so no problem. Please complete it out yourself, all right. The next example that I am going to look at is this question: find an orthonormal set in R3 containing 1 to 1, all right. Solution. So, let x, y, z belong to R3 such that inner product of x, y, z with 1 to 1 is 0. I want an orthonormal set. So, I want everything perpendicular to each other. So, it has to be perpendicular to 1 to 1 also. So, I am looking at that condition. So, this gives me that x plus 2y plus z is 0, or therefore, what I get is, if I write the vector x, y, z, this is same as x is same as minus 2y minus z, y and z, which is same as y times minus 2 1 0 plus z times minus 1 0 1, fine. So, check that. So, exercise, verify minus 2 1 0 is orthogonal to 1 to 1, unless I have done a mistake. So, it is okay, yeah, it is correct. Minus 1 0 1 is orthogonal to 1 to 1, that is also true, no problem, everything is okay, fine. But so, what I have done is that I have got this vector, using that vector I have got two vectors here. So, two vectors which are perpendicular to these, the given vector, all right. But these two vectors themselves, two vectors, these vectors are not orthogonal, all right. So, I will have to make them orthonormal, all right, orthogonal I have to make them. So, I will have to do some work. So, let me define things now, all right. So, I have something, so I can define it. So, define, so let u1 is equal to 1 to 1, u2 is equal to minus 1 0 1 and u3 as minus 2 1 0. I am using this. So, I already know that these two are perpendicular. So, I define w1 as 1 to 1 divided by root 6, the length, w2 as minus 1 0 1 divided by root 2. Let us compute V3. So, V3 is u3 minus u3 w1 w1 minus u3 w2 w2, which is same as minus 2 1 0 minus u3 with w1. So, this with w1, which is already 0 for us, there is no problem, just look at it, that is the way we have constructed. So, that part is 0 minus u3 with w2, all right. This is the one that is creating the problem for us. So, let us look at this part. This root 2 will give you twice, so it will become 1 upon 2. Dot product, this will be minus 2 into minus 1 is 2, and this is 0, so it is 2 upon 2 of minus 1 0 1. So, this is same as minus 2 1 0 minus of minus 1 0 1. So, minus 2, so this is equal to minus 2 plus 1 is minus 1, 1 minus 1 is 1 here, and 0 minus 1 is minus 1, all right, fine. So therefore W3 is equal to perpendicular, so you can write W3 as minus 1, 1, minus 1 divided by root 3, or W3 as 1 minus 1, 1 divided by root 3, whatever you want you can do that. Is that okay? So that's the way we get these things, fine. So I want you to understand this very, very important thing, that you can do these calculations, fine. Now I want to go to what is called an QR algorithm. QR algorithm. This was one of the milestones for us, QR algorithm. So we had done what was called the rank factorization, LU decomposition. The next idea was QR algorithm. So we are doing the QR algorithm. So I've got a matrix A which is M cross N, fine. So first let's assume that the rows are assume the columns of A are linearly independent, all right. So they are linearly independent. So I have got A as say U1, U2, Un. I can apply Gram-Schmidt to S, which is U1, U2, Un. If I do this, what happens? This will give me a set of vectors. So I will get a vector Q which will be W1, W2, Wn, all right. So Gram-Schmidt said that I get start with S which is linearly independent will imply me a set which is W1 to Wn, an orthonormal set. This is what the Gram-Schmidt process gives. So whatever that orthonormal set I have, I take Q as that, fine. Since this is an orthonormal set, so therefore if I want to look at QQ transpose and Q times Q transpose Q, this will turn out to be an identity matrix. Why? Can you think about it? So if you compute Q times Q transpose, look at this, you get W1, W2, Wn, these are the vectors, column vectors, and I have got now W1 transpose till Wn transpose. So this in one side gives me W1, W1 transpose plus so on plus Wn, Wn transpose. I don't know what this is, I cannot make anything head or tail of it at present, fine. But what we can do is that if I look at Q transpose Q, fine. So Q transpose Q will be W1 transpose, W2 transpose, Wn transpose, W1, W2, Wn. So this will be, look at the first column, first row, it is W1 transpose W1, W1 transpose W2, W1 transpose Wn, then it is W1 transpose W1, W2 transpose W2, W2 transpose Wn, and so on till Wn transpose Wn, Wn transpose W2, fine. Now we have been saying that this set W1 to Wn is orthonormal. It means what? It means that length of this vector is 1, fine, length of this vector is 1, length of this vector is 1, all right. So this dot product W1 transpose W1 is 1, W2 transpose W2 is 1, Wn transpose Wn is 1, fine. And what happens to these vectors? If I look at these vectors or these scalars, W1 transpose W2 is 0 because the dot product of W1 and W2 is 0. So this is 0, 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 and so on. So I do get back identity with me. Is that okay? So since I get identity, so Q is invertible. So Q transpose is invertible means I get this part, and therefore this is also identity. Is that okay? So this is what is important, that you are able to write identity in terms of these vectors. W1, W1 transpose is a matrix, n cross n matrix. Each of them is an n cross n matrix, all right. And since W1 to Wn are independent, these matrices, each one of them have rank 1, and I have written In identity as sum of n rank 1 matrices, fine. So let us look at this. So what we are saying is that I am looking at this matrix and trying to understand now what it is. So what we have done is that I have got a matrix A, I have written it as, from here I have got what is called Q. I want to relate A and Q. I want to relate A and Q as such relation. All right. So let us understand this very, very important thing. What we have, so if I look at Gram-Schmidt's, it tells me that linear span of U1 is same as linear span of W1, linear span of U1 U2 is same as linear span of W1 W2, linear span of U1 U2 U3 will be equal to linear span of W1 W2 W3 and so on. This is what it says. I have the matrix A as, so A is U1 U2 UN to me, fine. The matrix Q for me is W1 W2 W3 till Wn to me, fine. So since it says that linear span of U1 is same as linear span of W1, if I multiply this on the right by a matrix, so if I let me multiply this matrix here, I will get something here 0 0 0. If I look at this matrix, so I am trying to write this matrix as R, I am looking at Q times R, all right. Now since I am multiplying R on the right of Q, so I am doing column transformations. So it means that I am multiplying a star to W1, 0 to W2, 0 to W3 and so on, fine. Since I know that linear span of U1 is W1, this implies that U1 is equal to some alpha 1 times W1, all right, fine. So what I get here is that this matrix, R matrix that I am looking at, it has alpha 1 here, fine, 0 0 0, fine. Now this part tells me that, fine, that U1 is already a linear combination above, U2 is a linear combination of, U2 is some alpha 21 times W1 plus alpha 22 times W2. So U2 belongs to linear span of W1 W2. So I can find alpha 21 and alpha 22 such that this will happen, fine. So therefore when I look at matrix product again, I can write here alpha 21 here, alpha 22 here, 0 0 0, because then I can say that it is alpha 21 times W1 and alpha 22 times W2. Similarly, when I go to U3, I will get some alpha 31, alpha 32, alpha 33 and 0 here. In general, at last stage I will get alpha NN and alpha N1, alpha N2 and so on, fine. So this is the way the matrix R is to be obtained, fine. So you can see that I can get, so what I have here is that I have matrix A, I have got QR, Q is orthonormal, and not only that, Q transpose Q is identity, is same as QQ transpose in this special case because of Q or A being invertible, or A has full rank, all right, full column rank, so A has full column rank. I didn't say about M, I am talking only about N, full column rank I am talking about, fine. And R is, look at R is upper triangular. Fine. This is one thing. The other thing that you should understand here is that I don't have to solve a system of equation here. If I want to get alpha 31 is nothing but inner product of U3 with W1, because W1 to Wn was an orthonormal set. So each of these scalars which are in the linear combination, they are nothing but things like this, fine. They just come from the inner product. So you can compute them directly, you can put it here. So nothing special about it, fine. So this is about QR algorithm for this setup. But if I want to have a general setup, so let's go to some example where I had an issue. So there was an issue here, yeah. So here was the vector. So look at this example here where I have a problem. that if I have something like this, where the columns of the matrices that I am going to take, they are linearly dependent. So, if I take a matrix A, where I have got u1, u2, un, and the columns are linearly dependent, then what will happen is that the matrix Q that I will get it as, it will be W1 to WR, where R is equal to rank of A, all right. I will not get N. So, we will not get N of them due to linear dependence, all right, fine. So, what will happen is that I have got only R of them, so I have to maintain everything with that. So, I again write U1 here, U2 here, UN here. Then again I can write it here as W1, W2, WR. Now, this matrix will not be nice, but it will have some property, because look at this, this is R of them only. So, I need only R here as such, fine. So, it will be an R cross N matrix, all right. So, this is starting with an M cross N matrix. So, this is of size M cross R cross N, so that I got M cross this, and R here is less than equal to M. So, R is less than equal to M, fine. So, depending on, so W1, if W1 was already U1, I have something here. If linear span of W1 was equal to linear span of U1, then I will get a star. So, Q11, so not Q11, R11 will be non-zero, else it will become 0, all right. So, otherwise I will get zeros here. So, if LS of W1 itself is equal to LS of U1 and U2, implies that U2 is equal to some alpha times W1 itself. So, I will just get alpha here, 0 here, 0 here, 0 here, all right. So, it will not be an upper triangular matrix, but it is not a square matrix, it will be upper triangular form. The diagonal entries may be 0 here, all right. So, this is what you have to be careful, that when you generalize, some issues will come, but what is more important is, look at this matrix, this is an M cross R matrix, and this is the matrix Q. So, if I look at Q transpose Q, this is R cross M, this is M cross R, and you can check the way that I have checked that this is an identity matrix, all right, fine. So, we have been able to get a matrix, write A as QR, R has an upper triangular form, and Q is orthogonal with Q transpose Q is IR, fine. Now, why do we need orthogonal matrices? Basically because the norm does not change, all right. So, that is all for now. Thank you.